with this one. Okay, so first off, the domain. What can't happen here?
Zero.
0. X cannot equal to 0, but can equal anything else, right? So my domain is going to be from negative infinity to 0, union with 0 to infinity, right? All right. X-intercepts. So x-intercepts, we plug in 0, right? So 0 equals x minus 3, so x equals 3. So we got an x-intercept at 3, 0.
Hey, how many then?
Okay, 10.
That's it?
Yeah. Well, no. 16. So I've got x-intercept, I got 3, 0. Y-intercept, what do I get when I plug in 0 for x? Thanks a lot. It's undefined, right? So there is no y-intercept. So what is happening at x equals 0? Got a vertical asymptote, don't we? So x equals 0 is my vertical asymptote. All right, what about horizontal? And when I say horizontal asymptote, I should have put SA or HA because it could be a slant asymptote there as well. But in this case, it's going to be a horizontal asymptote. Why do we know we're going to have a horizontal asymptote here? Do you remember what?
Because upper will be lower and lesser than.
Trying to you're thinking too deep about this. It's because if you compare the degree in the numerator with the degree in the denominator, they're the same, right? So in this case, what's the leading coefficient in the numerator? Leading coefficient in the denominator? So my horizontal asymptote is y equals 0. No, y equals 1, sorry. Y equals 1, because it's 1 over 1. Does that make sense? Mm-hmm. Okay. It's been a while since we've done that. It was called end behavior. Remember, if your degree in your numerator is greater than your degree in the denominator, you don't have a horizontal asymptote. You have either a slant or oblique asymptote. And then you've got your, if your degree in the denominator is greater than the degree in your numerator, what is it? If your degree in your denominator is greater than your degree in your numerator, it's y equals 0, yeah. So let's move on. Let's get into the critical numbers. So let's take the derivative of this function. So it's x times 1 minus x minus 3 times 1 over x squared. So we get 3 over x squared. So I don't have a critical point, but I do have a point where we could change from increasing to decreasing or vice versa. And that would be at 0, right? So let's think about what's happening. Put 0 on the number line, plugging in a negative number or a positive number, it doesn't matter because it's squared. So this graph is always going to be increasing. So critical numbers, I'm just going to put check x equals 0, and we see we're increasing from negative infinity to 0, and then 0 to infinity. Decreasing, not applicable. Are we good to keep going?
What is
Alright.
check 0?
Say that again.
What is check 0?
Well, zero's not in the domain, but I could change there.
Mhm.
So I was gonna check at x equals 0, so that's the reason I put 0 on the number line.
Okay.
Even though it's not a point on the graph, it could change there.
Okay.
Point of inflection, second derivative, f double prime of x low d high is 0 minus high d low is 6x, and that's over x to the fourth, so we get negative 6 over x cubed. So again, it's not a point of inflation because it's not a point on the graph, and I'm going to check x equals 0. Now, what happens here? If I plug in a negative, I get a positive, right? So I'm concave up. And then if I plug in a positive number, I get a negative, so I'm going to be concave down. So my intervals of concave up are negative infinity to 0. Intervals of concave down are 0 to infinity. So this time in my chart, I really only have one thing of interest, and that's at 0. So negative infinity to 0, 0 to infinity, f prime of x, f double prime of x. Now, what did we say was true as far as the first derivative was concerned here? It's increasing, right? Okay. Now this is increasing in concave up. And then this is increasing in concave down. I don't know why in the other ones I put arrows, and then this time I decided I would spell it out. So increasing in concave up takes on this shape, increasing in concave down takes on this shape. All right, so now when I graph, I don't just have points to plot in, I have some asymptotes to plot in as well. So what are my asymptotes? Well, I have a vertical asymptote at the y-axis, so I'm just going to put a dotted line there. And then I have a vertical, sorry, that's my vertical asymptote. I don't know what I said last time. Horizontal asymptote is at y equals 1. So I'm here. Okay. Now, any interesting points? Really, the only point I came up with on this entire graph was the point 30. All right. So, now I have to consider my asymptotes, and when I graph the asymptotes, I need to make this shape right here conform to my asymptotes in either the third or the fourth quadrant. Now, looking at what's happening here, if I've got this shape right here, I'm going to be looking at being in the second quadrant portion, so it's going to take on this shape here. And then if I'm in to the right of the y-axis, I'm increasing and I'm concave down. And I also need to pass through this point right here. So again, trying to hug up against the asymptotes as much as possible. And it goes something like that. So that's gonna be essentially what the graph of, y equals, or f of x equals x minus 3 over x. So let me get y'all to try number 4 on your own. So that's section 3.5.